Hello and welcome to the second in our series of 3 winterization webinars brought to you by Edmonton Valve Fitting, suppliers of crucial fluid systems throughout northern and central Alberta. At plants and facilities where gases or liquids are processed, low temperatures can mean ruptured tubing or other problems that will stop production, leading to unwanted downtime, unplanned labor costs, and all kinds of other headaches. This series of winterization best practices is designed to help make it easier for professionals at plants and facilities to get prepared for those low temperatures and to avoid potential problems. I'm your host, Fiona Hughes, and with me to present today's webinar is Tristian McCallion, who this week will be discussing steam trap stations for tracing. Tristian is a local field service advisor at Swagelok Energy Advisors, based out of Edmonton Valve Fitting. The Swagelok Energy Advisors team of field engineers are on site with customers 3 out of every 4 weeks, providing steam system advice, training, and solutions that increase the performance of customers' fluid systems. Today's presentation lasts about 30 minutes, after which we'll address your questions, so do please jot them down in the chat window so we can answer them at the end of the session. We'd also love to have your input on what other webinar topics you'd like to see us address, so do please write in with those thoughts too. Our session today is being recorded and you'll be sent a replay link should you wish to make this information available to your colleagues. So now, without further ado, I'll hand the mic over to Tristian McCallion to get us underway in discussing steam trap stations for tracing.
Good morning or good afternoon or aloha to all of you out there. I see we've got a couple of people even in from Hawaii today, so welcome to our winterization series and continuing on our presentation from last week where we talked about tracing. This week we're going to talk a little about steam trap tracing stations and trap testing. Okay. If we remember from last week, a lot of the focus that we had was on the tracing systems themselves and what they did and how to tie them in, how to actually connect those tracers to the main lines. And if you remember back, we had 2 primary functions for our tracing lines. They were to replace the heat lost from the process fluid in the system, which could be a result of poor insulation or other components in the system where the heat could escape, and also for freeze protection, which in the Edmonton environment is probably not too far off. We had a couple of nights this week where we were dipping down around the freezing point, so time to definitely start thinking about this and make sure our systems are operating at maximum efficiency to keep ourselves competitive on the global stage. So we've talked about the tracing system itself and how we tie in on the lines last week. Now what we want to do is actually talk a little bit more about a couple of the components that are in the system, and then we're going to talk about the supply trees and the return trees. So if we're looking at a drawing like this is a typical tracing application that we're looking at. And what we're looking at here is if we're starting off, this is our supply line here. And one of the things that we want to make sure of is when we're coming in off the steam supply line, we want to make sure that we are supplying the steam from a dedicated source. Okay? We don't want to have the tracing lines pulled off of a process line or off of some other line where we could shut the system down. So example, if I'm running a steam line to a heat exchanger, I want to make sure I'm not pulling my steam supply off of that line that's going to the exchanger, because if I need to take that exchanger down and do any maintenance on it, then I run into the problems. If I shut that steam line down, then I have to shut my tracing line down. So typically we want to come off a dedicated line that's going to be up and running all the time that we're going to have that tracing system on. After we come across and pull the line off the supply, we're going to take a short jumper and connect it to the actual pipe. We're going to run along the pipe, and then when we're going to come off at the end, we are going to return to our condensate return header. So the condensate comes off and returns to the condensate return header. We've got some choices when we're designing these systems that we can either run a supply tree, is a common terminology for it, where we group all the supply valves and all the condensate return header valves together, or we can run them individually. So it depends a little bit on how your plant's set up, how many tracers you're looking at, and the proximity of the lines that you're running. Generally speaking, the more efficient system is going to be one where we can run the headers together. As soon as we start to spread things out, we add problems with testing. It's harder to find the traps. By having everything together, it certainly makes it a lot easier to do maintenance, to do testing, and even for the installation at the first time. We may have to have a little bit more tubing there in order to connect in, but tubing is a relatively minor expense when we're looking at the overall picture of our steam supply for the tracing headers. Again, when we're looking at the tracing headers, this is a typical sort of configuration that we're going to look at. On the left-hand side, we've got our supply, and on the right-hand side, we've got the return side. Generally speaking, the main difference between the two is going to be the presence of a steam trap on them. On the supply line, we want to make sure that we're coming off with a good quality valve, make sure that it's selected for steam application, so we do have the correct temperature and pressure ratings on them. At the bottom of the header, we're also going to make sure that we're going to have a steam trap installed there, so you can see that right at the bottom of the header. Even the condensate supply line, or excuse me, the steam supply line is going to have that steam trap station installed at the bottom. So if there is condensate that builds up, obviously over time condensate is going to start to pool up in the bottom of this header here. So we need a way to remove it out. So we have to make sure we do have a steam trap station at the bottom of that supply header. The other thing we want to look at when we're looking at the supply header is to make sure that it's sized correctly. When we're dealing with steam systems, we want to keep velocity fairly low. And if we start to increase the flow without increasing the size of the header, we're going to generally increase the velocity that we're going to see. The problem that can occur if we start to increase velocity is it becomes tougher and tougher to remove condensate out of the system. And the condensate can get passed down the line and result in water hammer. So that's generally going to be your supply side. On the other side of it, after the steam's gone out, been run along the piping to give up its latent energy to heat the process up or prevent the freezing, now we have condensate in the system, and we have to, again, get that condensate out to make sure we are maximizing the efficiency in our system. So what we're going to do is we're going to have a configuration, something like this. It can be vertical, it can be horizontal, just depends on how we're setting our lines up. And in this case, similar to the supply header, we're going to have a primary block valve, which is this valve right here. We're also going to have our steam trap, which is the device right in the middle. Quite often we see a secondary valve with the block and bleed requirements that we're starting to see out there from OSHA or from any of the safety organizations. By being able to double block the trap in, the trap's going to be a fairly heavy maintenance item, so we want a way to be able to get it in and out fairly quickly. So that double block system is going to allow us to do that. We're also going to have some kind of blowdown on the system, which is the third valve that you see on the header right here. And we'll look at the headers in a little bit more detail here in a minute. But when we're selecting and setting these systems up, there's a number of questions that we have to ask ourselves. We have to think about how are we actually going to connect to the steam header. Is it going to be a welded system? Is it going to be a threaded system? Generally, we try and avoid pipe threads in the system. Tubing systems, welded systems are going to give us much better performance. A thread in a steam system is just a back weld basically waiting to happen. We're going to see leaks in them. The expansion and contraction that we see in the system just lends itself to leakage when we have threads in the system. We have to ask ourselves, do we need lockout and tagout? What's the plant requirement there? Can we use ball valves with a lever handle, or do we need an oval trip-proof handle, or do we need even more of a positive lockout mechanism on there? So again, depending on the type of valves that we want to use and how we're going to set them up. Do we want to try and keep the supply header and the return headers close to each other? That's going to be more a function of the physical layout of your plant. Wherever possible, it's best to keep these headers as close together as we can. Simple reason being, as we talked about startup last weekend, you can imagine if I'm starting off my first valve on the top of my supply header, this valve up here. I open that valve up. I've got my blowdown valve or my condensate return valve on this side. Now if I'm starting the system up, the way that I'm going to do that is I'm going to open up my blowdown valve, which is the bottom one, allow any of the steam and non-condensables to blow through there. I'm going to open up my supply valve to push any of the condensate through the system, and as soon as I start to see live steam coming out of this valve, I'm going to isolate it, so shut that one down and connect the system back in. Now if these headers are spread apart several hundred feet or several hundred meters, then obviously we're going to need more than 1 or 2 people to get the system up and running. Whereas if I can keep these headers within maybe 10 or 15 feet of each other, then there's a good chance that I'm going to be able to manage the system and bring those tracing lines up one by one by myself to make sure that we are running the system properly. We want to look at the flow that we're going to need in there, and are we designing for future growth as well? So do we want extra ports on the headers, or are we just going to have a standard header that we're going to plug in? And then when I need another one, I've got a standard configuration to run it along there. We're also going to make sure that we are insulating these headers too. A couple of reasons. One, it's a fairly large surface area, so there is a potential for a lot of lost energy coming out of these headers. The other one's going to be for personnel protection. These headers are generally going to be in an area where people can walk by them. They need to be fairly accessible as we're starting the lines up and bringing them down at least a couple of times a year. So they have to be accessible to personnel, but we also have to protect personnel from accidental contact with them. So we want to make sure that the lines are insulated to allow for that as well. And then the last thing we're going to want to look at is make sure that we are standardizing our components. You know, you go around a lot of facilities where they've been in place for 15, 20, even more years than that. And the number of different valves that you see out there, the number of different connections that you see out there is mind-blowing. The problems that causes is when I go to stores and I have to repair or replace a valve, now I'm looking at a system where we have to have multiple suppliers in the warehouse. If I can standardize on one valve, in that case, it's much easier to just go and grab a valve from the stores. I don't have to carry 5 or 6 different manufacturers. My costs are dramatically reduced that way. So if we look at the steam trap station itself, it's going to be made up of a number of different components. This is the typical one that we really like when we're doing our design work with Swagelok Energy Advisors. So what we're looking at here is a flow direction can either be left or right. In this case, we're coming in from the left, exiting on the right. So I have my primary isolation valve. Let's get my annotation going again here. So my primary isolation valve is this guy right here. My steam flow is coming in this way. So I open my primary isolation valve, and that brings me to a 2-piece solution to connect my steam trap into the system. It's a universal mount assembly which remains permanently mounted in the system. That piece never ever comes out. Every steam trap manufacturer out there will make a steam trap that does mount up to this universal mount assembly. What it allows us to do is have a standardized dimension and a standardized footprint to put whatever trap we need into or take it out of the system. The way it's connected is with 2 bolts and a spiral wound gasket. That's easier to say than I thought. But so when we connect that in, now all I have to do is isolate shut my 2 isolation valves, open my blowdown valve to depressurize the cavity inside the steam trap, and then it's 2 bolts on, 2 bolts off, I'm back up and running again. So we highly, highly recommend the use of the universal mount, regardless of whether you're using isolation valves coming back into your header or not. The universal mount is something that we would strongly, strongly recommend. The steam traps itself, we're going to talk about those a little bit later on, but that steam trap will mount up to this universal mount down here. The other thing that we really want to make sure that we have either in front of the universal mount or connected to the universal mount is a strainer. Strainers are crucial to have in the system. One of the main reasons that traps are going to fail is because you have dirt or corrosion material accumulation is the new politically correct term for that in the system. One of the things that we find with strainers is if you don't have a blowdown valve on the strainer, the chance of having that strainer opened and blown out is very, very low. Even with a blowdown valve on the strainer, it's pretty rare that you see people actually opening these valves up to blow the strainer out and clean it out. It is a maintenance item. Every time we're testing these traps, we should be cleaning those strainers out and blowing them down. So wherever we have a strainer, we want to make sure we have that blowdown valve installed. You can get some strainers that have the built-in plug that you can loosen off and allow the dirt and the non-condensables and the other material to pass through that way. The issue that I find with that is now you're putting your hand very, very close to the stream that's coming out of there. And even if the system's down or it's cooler than the actual steam operating temperature, you're still potentially dealing with very hot condensate coming through there. So there is a definite burn risk by doing that. So by putting in the valve with a handle that's removed from the flow path, we find that the safety is dramatically increased. The 5th component that we see on the steam trap station is the test valve, or the secondary isolation valve. So what we're looking at is this guy right here, and this one is a multi-purpose valve, it's not only acting as the isolation valve, it's also acting as the test valve. Again, very nice use of space. It keeps everything nice and compact. So what we'll find is when we shut this valve down, shut the test valve, the steam that's coming through, or whatever's coming through my steam trap, so it'll flow into universal mount, up, out, into the steam trap. The steam trap will decide if it's condensate or live steam, in which case it'll either open or shut accordingly. It'll then allow the condensate to pass through, and if we shut this valve, that condensate will be directed out my test port. So I can actually see, physically see what is happening with that steam trap. So now if I'm trying to do any testing with the system, it'd make it a lot easier to do. Once we've jumped either from the steam supply header or returning back to the condensate return header, again, we're going to need to make sure we're insulating our lines. Easiest way to do that, we find, is with pre-insulated tubing. PIT is another terminology for it. Fairly common out there. Comes in endless coils up to 500 feet long. So we minimize the connections, we minimize the potential leak points. You plug it in, the engineering is being done to make sure we have the correct insulation in there. We also have the lagging on the outside, which is either going to be a PVC cover or a urethane cover, depending on the temperature range that we need it to meet. The other thing that we have to make sure of, in these pictures here, it kind of shows you the bare insulation. You see the tubes running in, and then we have the bare insulation coming out. So what we're looking at right here on the edge of the tubing is the bare insulation. We can't have that when we have it actually installed. So we have to put some kind of sealant over that to prevent that insulation from being exposed to the environment. And you can get heat shrink boots, you can use tape, there's all sorts of caulking, different things like that, that we can use to prevent that insulation or that fiberglass from being exposed to moisture and other things which are going to degrade the quality of the insulation and reduce the insulation effectiveness. So we absolutely have to make sure that we are covering those off. We also want to make sure that when we are selecting our components that we are obviously meeting the bare minimum of the ASME codes that are the guiding principle between a lot of the design. B311 is the predominant code that we see out there. Local authorities are going to probably going to use some variation of it. And all it's saying is that we are selecting materials that will meet the design pressure, temperature requirements of the lines that we're running. We talked about valves last week. As an absolute minimum in the steam world, we really recommend that you select a Class 4 shutoff at a minimum. And from last week, hopefully you remember that Class 4 shutoff allows 0.05% of the rated valve capacity to come across that valve seat at any given time and still allow that valve to be operating correctly. Okay. Fittings, tubing size, and material, let's standardize on all that. Let's make sure we got the correct installation in there. I talked about gauges a bit last week as well. And again, gauges are a very, very inexpensive way to troubleshoot and diagnose your system. If I know that I've got a 100-pound steam system and my pressure gauge is showing me 100 psi, my temperature gauge is only showing me 310 degrees F or 150 degrees C, then I know I got a problem. I got something wrong with my steam system. Maybe I've got air entrapped in it. Maybe some of my components aren't working quite properly. It's a really, really good diagnostic tool that allows us to find out what is actually happening in my system. And then the last thing we want to do is make sure that we are specifying the correct steam traps. And we'll talk a little about steam trap selection towards the end of this presentation. Okay. When we get into testing steam traps, one of the questions we get quite often is, what is the best way to test traps? And the simple answer is use all of them. All the potential methods or all the methods that you have available to you. Three primary ways of testing steam traps, or three tools that we can use for testing steam traps. We're going to have temperature as one of our tools. We're going to have audible or ultrasound to test. And then the third way is going to be visual. And we can break the visual down into a couple of different methods as well. So visual can either be through the use of a sight glass, kind of like you see on the right-hand side of the page. Oops, stop doing that. So something you see on the right-hand side of the page, right in front of those big flown thermostatic traps, kind of between the two flanges there, you can see a series of 4 or 5 sight glasses, so you can see what's actually happening inside the pipe. Or if you look at the bottom left-hand picture, you can see a test valve installed with the live steam being blown out. So again, my preferred method whenever I'm testing traps is if there's some way to do a visual test, that's what I'm going to go with. And there's a couple of reasons for that. The temperature guns are very effective at telling us if the line's plugged up. So if I know I'm running a 100-pound system, there's a constant relationship between 100-pound steam, or the pressure of the steam, and the temperature of the steam. So I know 100-pound steam is 338 degrees Fahrenheit, 170 degrees C. If I go in and I'm testing that line, and my steam temperature, or the temperature of that line, is down at 250 degrees or 230 degrees or lower than that, then I know I don't have 100-pound steam in my system. Maybe I'm plugging my line up, I'm building condensate up, I'm reducing the amount of heat flow. So it's telling me I got a problem. So on the side of testing for the trap being failed in the closed position, then yes, I can use temperature for that. The problem is on the downstream side of that trap, if that trap has failed in the open position, temperature will not tell me if that trap has failed open. It'll just give me an indication of whether or not I have live steam getting to that trap. The other non-intrusive method is the ultrasound, and that's the top right-hand corner there. There's a number of different tools that you need in order to do that. It does require a little bit of training, but it's relatively simple to use. The negative with the ultrasound is it does require the interpretation. And what I find is when we're in plants and talking with people, if I go in with my ultrasound and my temperature and I can test a trap, and I'm probably 99.5% accurate with my testing. I've tested tens of thousands of traps over the last 10 or 15 years that I've been doing this. So I'm reasonably accurate just from the experience and the opportunities that I've had to go out and test these different traps. But I can tell if I go to an operator whose system isn't running properly and he thinks it's the steam trap or she thinks it's the steam trap that's causing the issue, I can go in with all my diagnostic tools, my infrared, temperature, my ultrasound, test it, and yep, that trap's working fine. But if that operator's process conditions don't improve, they're still going to blame that trap. They don't really understand exactly what we're doing with the temperature with the ultrasound. What I found is if I can open up a valve and show them what is actually coming through that steam trap and explain to them how the trap works, then they tend to believe me a little bit more. So if I have a test valve installed in the system and I cycle that test valve, and it's an on-off trap like the one we have in the picture on the bottom left-hand corner, and you can see that distinct on-off cycling of live steam being blasted through and then having the system shut down so there's nothing coming through. It's a definite and a very, very obvious indication that that system is working properly. Sight glass is a little bit tougher because you kind of got to look for the steam or you got to look for the condensate, and steam being a dry invisible vapor. If you don't see anything in there, maybe the system's plugged up, maybe you're just seeing the vapor coming through, so maybe it's blowing through. But again, the sight glasses are non-intrusive. You don't have to worry about getting hot steam being ejected out into the atmosphere, which you have to think about a little bit with the test valves. You have to make sure you are discharging into a safe position. When I am doing ultrasonic testing, the way that I'm going to do that, the first thing I'm going to do is check with the temperature gun to make sure I got live steam coming to the system. As soon as I've done that, then I'm going to test the steam trap, and I'm going to test it at 3 points. In this particular example here, my steam flow is coming from the right-hand side and going to the left. So my steam flow is coming this way. So I should have condensate on this downstream side. So I'm going to come in and test 3 points. I'm going to get a baseline reading right here at point A, and that's going to tell me how much noise is in the system and just eliminate the background that we're going to see. At the middle point here, just on the outlet of the steam trap at point B, I'm going to listen to see what's happening in the steam trap. And it should be quieter. I should hear a distinct on-off cycle if it's an on-off trap to tell if that trap's working. If it's not giving me a distinct on-off cycle and the noise level is higher at B than it is at A, then I can start to think that maybe that trap has failed in the open position. To confirm that, I'm going to do one last check down at point C. And what I'm looking for at point C is for it to be either quieter or louder than at point B. Ultrasound is going to be the loudest at the point of generation. So if point B is louder than point C, it tells me that the majority of the turbulence or the ultrasound is coming through a restriction, which would be the orifice of the steam trap. So I can tell that that steam trap has failed in the open position. To know when we're testing traps, be it visual or be it with sound, is what is the trap design and how does it function. And when we're testing traps, there's two main functions or two main classifications that we are going to look at. And that's going to be continuous flow or on-off design. And we're very fortunate with steam traps that it's a fairly simple way to break them down. The flown thermostatic trap, which has a very distinctive shape and size, is going to be the only type of trap that we have or that we look at that has continuous flow. So this is a cross-section of a flow and thermostatic trap, and the way that this trap works, just bring my annotation back up here again. So the way that this one works is my live steam or condensate will flow in to the body of the trap and start to fill this area up. As the condensate rises, it's going to pull this float up and pull the valve stem here away from the seat and allow the condensate to pass out of the system. Okay, as we increase condensate, the valve or the ball rises higher, opens that valve a little bit more and allows for more condensate to flow through. So when we're testing visually, what we're going to look for is kind of a continuous drip of condensate or a flow of condensate coming out of there. We don't want to see just vapor coming through. Remember, steam's a dry, invisible gas. So if I open up my test valve and I don't see anything, but I hear the whistling and maybe I start to see a little bit of a water vapor plume a few inches or a few feet away from that valve or the discharge nozzle of that valve, then I can tell I got live steam blowing through, so that trap has failed in the open position. But what I should see is just some liquid and some condensate flowing out of there with a little bit of a lazy flash vapor coming out as well. Okay, so that's the flow and thermostatic design. Continuous flow, that's what we should look for. If I'm testing with ultrasound, this one's probably the toughest one to test with ultrasound because there is some continuous flow. We don't have that distinct on-off cycle. We can do it, but we're doing more of a judgment call on these ones, and the training is becomes more and more important if we're dealing with a large population of flow and thermostatic traps. These traps can range in size from something the size of a water bottle, 500 milliliter water bottle, right up to 3-4 footers that are handling thousands of gallons an hour of condensate coming through. Okay. So that is the only type of continuous flow trap that we look at. The rest of the traps that we look at are all going to be a distinct on-off cycle. And these are probably the traps that most people are familiar with. They're going to be the inverted bucket, the thermodynamic discs, and the thermostatic. So we'll quickly run through those, show you how these guys work, and then we'll jump into a few questions. So the first type of the on-off trap we're going to look at is the inverted bucket. Again, on-off design. So my steam flow comes in on the left-hand side. I'm going to get steam and condensate flowing in. It'll drop down and fill up the body of the trap. The name inverted bucket comes from the name of this bucket-shaped piece here. You can see the live steam filling up the top half of the bucket. And what it does is as the steam comes in, it increases the buoyancy of the bucket and pulls that valve stem in against the seat of the trap. Over the next 15, 30 seconds or so, the steam inside that inverted bucket is going to give off this latent energy. It's going to go back to the condensate state. It's going to change phase back to the liquid. And the weight of the bucket is going to overcome the differential pressure at the valve seat, dropping down, allowing the condensate to blow through until live steam comes back in, fills that bucket up, and closes it off. So it's a fairly quick cycle. You'll probably see this trap cycle anywhere from once every few minutes to maximum we want to see is maybe 4 to 5 times a minute. And we should see a distinct on-off cycle with a distinct blast action as it allows that condensate to pass through. Okay, so that's an on-off trap, is the bucket trap. The next type of trap we'll look at will be the thermostatic trap. And similar to a flow and thermostatic trap, there's an element inside it that will allow, that when it's heated up, it's going to expand or change shape and force the valve stem. What I'm seeing is my live steam is the orange coming in. I've got a bellows shaped here, which is a liquid-filled bellows, which will expand out as it gets heated up. So as the live steam comes in, heats it up, the liquid inside that bellows expands and flashes and drives the valve stem into the seat. And then as it cools down and condensate builds up, the liquid inside the bellows condenses back down, collapses the bellows, and allows the steam and condensate to pass through. And so again, a distinct on-off cycle. These traps may be a little bit slower cycling than the bucket traps, so maybe once a minute, twice a minute, maybe a little bit more, but you should still see a distinct on-off cycle, and if you're testing with ultrasound, you should hear a distinct on-off cycle as well. The last type of trap we'll look at is the thermodynamic trap, and the thermodynamic trap is a very, very common trap in tracing applications. They're small, they're inexpensive, they're fairly robust. The biggest negative with the thermodynamic is they're not the most energy efficient. They do consume a fair bit of live steam as they're operating. Even if when they're operating correctly, they are going to consume a fair amount of live steam. The way that it works is there's a disc that sits in there. You can see it in between the set of arrows there. And as the live steam flows into the system, the steam will come through, up, and surround that cavity, pressurize that cavity. And because the air on the bottom, or excuse me, the steam on the bottom of that disc is flowing at a higher velocity than the steam on the top, it creates a lower pressure area which actually sucks that disc down against that seat and closes it off. Over the next 5 to 15 seconds, the steam that's left in the top of that cap radiates out its energy, changes state from the gas back down to the liquid, and then when it does that, it condenses in size significantly, about 1,600 times. When it does that, it reduces the pressure. When it reduces the pressure, it allows the steam pressure in the line, or the condensate in the line, to force that disc back up and then discharge the condensate through the outlet of that trap. So very, very distinct on-off cycle. You hear them referred to as blast traps, disc traps. There's a number of different names from them. Again, very robust. There's not a whole lot of components in there. They'll stand up to some freezing. They will, you know, the inexpensive nature of them makes them very, very popular in tracing applications. One of the things that's nice to think about too, though, when we're looking at these traps is the fact that you can get universal mounts for just about every type of trap that we've talked about. The bucket traps, the disc traps, the thermostatics, even some of the float and thermostatics we can get to mate up to the universal mount. And if we have that universal mount in there, it's going to dramatically decrease our maintenance cost in the system. A couple things just to touch on for the trap sizing and selection. When we're selecting traps for tracing applications, the tracing is generally going to have a fairly low condensate rate. We're usually looking 50 to 100 pounds per hour of condensate coming through that trap. So when we're selecting our traps, we want to make sure that we're selecting a trap with a very small capacity on there. Now, last week we talked about tracing lines being maximum of about 100 feet long. If we're running a tracing line where we have it gone above that, or it's an oversized tracing line, well, then we're going to want to make sure that we are calculating out how much condensate we are producing or how much live steam is being consumed by that line and size the trap accordingly to that. The other thing to remember and think about, and it's you know, this time of year when we're not quite at freezing temperatures, it's a little easier to forget about, is that if we are in an environment where we're doing freeze protection, we're obviously doing it because we can get below freezing. So what will happen to condensate if it's left inside that trap is that when it freezes, it's going to expand out. When it expands out, it starts to tear apart bodies and split connections. So one of the things that's very common to see out there on tracing lines is if you do have bucket traps, or if you have thermostatic traps or some other type of trap that's installed where there's a low spot in the line and condensate can pool, it's not uncommon to see these things that are being puffed up or swollen up, so they've been frozen and the metal's been stretched or possibly even ripped by the freezing effect of that condensate line. So if you do have traps that maybe have dead spots in them or low spots in them, we want to make sure that we can find some kind of self-draining mechanism on there. Some of the bucket traps, they'll install a little thermostatic element in the bottom of the trap that when the steam does cool down and we start to see condensate in the line, that thermostatic element will open and allow the condensate to drain out and run through. So we can help prevent that from happening. Okay, so I believe that brings us through the presentation. Are there any questions? Okay, I got one coming in here. It says, if there's a temperature differential across the steam trap, doesn't that mean that it's working properly? Not entirely. It's kind of giving you a half picture. So basically what we're saying is, I'm just going to back up a couple of pictures here. So if I'm looking at a picture like this and I'm testing on the right-hand side, that's my inlet side, and it's 100 psi steam system, and I'm getting my 338 degrees temperature rating on that. Yep, that's great. That's what I want to see. It means I've got live steam coming to the steam trap. If I then take my temperature a little bit downstream of that trap, even just immediately after the trap, and it's showing me 212 degrees F or 100 degrees C, it doesn't necessarily mean that that trap is functioning properly. What that is telling me is that my condensate return line is operating at or around 0 or 1 psi. There's a direct relationship between pressure and temperature and steam. And if I allow my steam to pass through a restriction and drop down in pressure, it's immediately going to take on that temperature characteristic of that lower pressure steam. So even if I'm running from a high pressure to a low pressure, even with a big temperature drop, it happens so quickly that I can't tell, even with a high-end infrared camera that will show us within a few degrees, I cannot tell that that trap is passing across. So in that case, I'd have to use ultrasound, or I would have to use an infrared device to check. Okay, so hopefully that one makes sense. Okay, another one's just come in here. Do you prefer sight glass or test valve for visual testing? My preference is for the test valve. The reason being, I mean, the sight glass is nice from the standpoint that we don't have to break into the line and we're not discharging condensate. So in some facilities where you have to get approval to open valves, yeah, the sight glass can be nice from that standpoint. The negative that I find with it is that if the trap is blowing through, it can be tough to tell sometimes if it's blowing through or if it's plugged further up the line and I don't have, or I've just got condensate sitting in there. You need some kind of movement in the line to get some sort of reference of what's going on. So if that's not happening, that can cause some problems for me. Whereas with a test valve, I open it up and either something's coming out or something isn't coming out. So it becomes fairly obvious. So from that standpoint, I really prefer the test valve, just so I can get a good visual indication. Sight glasses as well can cloud up over time. It's one more component that you have to put in there. If I use a test valve, then I can get isolation valves and test valves built into a single piece, so my costs aren't that much higher than adding those extra components. And to get some sight glasses that deal with the higher pressures, they can be very, very expensive. Okay. Anything else? Okay, one more coming in here. What type of trap do you prefer for tracing? That's you know, it's one of those things that we look at. Depends on where you are and what you're actually doing with the trap. So as a general rule of thumb, what we'll typically do is, if it's an on-off system, meaning that I turn the system on and I don't have a control valve in front of it, I'm going to use an on-off trap. So an on-off trap is going to be a bucket trap, a disc trap, a thermostatic trap. If it's something that has a control valve in front of it where I can modulate the flow, then I want something that can continuously discharge condensate. So float and thermostatic trap is going to be my first choice for there. So basically, if we're looking at it, for the tracing applications, then what we're looking at is an on-off trap, which would give us either the bucket trap, the disc trap, or the thermostatic trap. The bucket traps I find can have low points in them. So in that particular case, there's potential for freeze up unless we have that extra element, a thermostatic element in it. And that's, to me, that's just kind of one more thing that can go wrong. The thermodynamic or the disc traps, they're very robust, but they do consume an awful lot of live energy, so tend to steer away from those. So kind of the long way to get to the answer is the thermostatic traps generally going to be our first preference for this kind of application. I see there's a sort of a follow-up to that one. Is there a brand or a manufacturer that you prefer? And truthfully, no. And the reason that we don't usually talk manufacturers for the steam traps is there is such a variation in the distribution channel for these things that what can work extremely well for me here in Edmonton can cause all sorts of problems for you, maybe down in California or in Hawaii or Minneapolis or wherever your station's at. There's one manufacturer that Swagelok Energy typically uses when we do our design work is a thermostatic one. Kelly Paffel, who's our technical manager, he's had a really good relationship with the company for a large number of years, and it's the one that's shown in quite a few of our pictures there. The problem is the supplier here in Edmonton that we deal with isn't that good. They don't carry a whole lot of inventory. When you look for technical support, they're tough to follow up with. You know, the type of traps that they put in aren't always the best ones for the application. They may steer people the wrong way just because it's what they've got in inventory. So for me to recommend that manufacturer up in Edmonton, I'd have a very, very hard time doing it. There's a couple of other manufacturers where their products may not be quite as strong as this one manufacturer's products, but their distribution chain is much stronger. The product's always in stock. They have very, very strong technical support. So in that case, that's kind of what we'll look for. Okay. We've got a couple other ones coming in here. I've got one from California. Customer asked me, when insulating for personnel protection, is there a legislated maximum surface temperature specified anywhere? Canada, OSHA, I've seen both 120F and 140F mentioned in articles, but I can't find any hard and fast legislated number. From what I've seen out there, Up in Canada, we typically look at around 50 degrees C. It comes down to more of the burn time, how long it would take to actually get a burn on your skin from contact. And I have seen the 120 and 140 degrees mentioned in different articles as well. As a general rule of thumb, if you're getting up to temperatures where you are that hot and you could potentially burn people, then we want to make sure that we are insulating to make sure people cannot accidentally get burned. And it doesn't have to be insulation. Some of the traps that we deal with, like flow and thermostatics, they don't like to have insulation on them. There's still a very large surface area there. They tend to be low where personnel can get in contact with them. So in that case, we're going to build some kind of guard system around it. So it doesn't necessarily have to be insulation, but we have to be able to keep people away from the hot surfaces. Okay. I've got another one here. Please explain the bellows trap and how it functions. So bellows trap can come in. There's some element inside the bellows trap, or excuse me, inside the thermostatic trap that'll react to temperature change. It can be a metal element, it can be a wax, it can be a bellows that's filled with liquid. In this case, the picture on the screen is a liquid-filled bellows. So what happens with this one, inside that liquid-filled bellows is an alcohol. And the alcohol has a boiling point somewhere below the boiling point of water, or the liquid that we're using to produce the steam, because it's not just water in there. There's going to be some chemical treatment. There's going to be a few other things in there. So the boiling point is going to be right around that 100 degree C, 212 degree F mark. The liquid inside the bellows is going to flash to the vapor and expand out 2 or 3 degrees C below that, or 4 or 5 degrees F below that. So when I'm starting the system up, I'm going to have condensate and non-condensables flowing through here, and the bellows is going to be contracted in. So my valve stem here, let me see if I can get the sanitation to work again without blanking the screen out. Nope, sorry, it doesn't seem to like that. So what will happen is when I start the system up, these bellows are going to be contracted, and that valve stem is going to be pulled away from the seat. So any of the fluids, the liquids that are in there, the air that's in there is allowed to pass through very, very quickly. These traps can actually have a very high capacity comparatively to their size. So I can get a trap with half-inch end connections on it that can actually flow as much as some of the bigger bucket traps that may have 3 or 4 inch flanges on them. So there's very, very high capacity to size ratio with these traps. Then as the live steam starts to come into the body of the trap and starts to heat up, the bellows starts to take some of that energy, and it's heating up the alcohol that's inside those bellows. And about 2 to 3 degrees below the saturation temperature of the steam, so just before that steam becomes full live steam inside the body of the trap, the liquid inside that bellows flashes to the vapor, and when it flashes to the vapor, it expands out and pushes that bellows open and drives that valve stem into the seat. Now over the next 20 seconds, minute or so, the liquid or the bellows are going to cool down as condensate starts to pool up around it, and condensate backs up in the system. So as we see that happening, the bellows condenses down, the alcohol inside the bellows reverts from the gas back down to liquid state, the bellows contract, and allows the condensate to pass through. And that's kind of how the cycle works on that one. Okay, I've got another one here where I've got from John asking, can I have too many steam traps in the system? And typically no. The reason that we can't have too many steam traps in the system is because every time I have a tracing line, I have to have a trap on it. So the more traps I have out there, then the more efficient my system is going to be. I'm going to have less condensate pooling along. There are generally going to be prescribed points that we're going to have steam traps. So in the tracing world, every line is going to have a trap on it. So every time I come off with a supply line, I'm going to be trapping that steam before I return it into my condensate header. On the steam main line, every time I change direction, change elevation, I'm going to have a steam trap. If it's a straight line with no expansion loops or changes in directions, then about every 300-400 feet or so, I'm probably going to have a steam trap in there. But that gets into a little bit more engineering on that side of the house. So there are certainly prescribed points that we're going to have that. Anytime I got a valve that I can shut off, I'm going to want to have a steam trap in front of that one as well. Okay, so hopefully that answers that one.
Thank you, Tristian. That was excellent advice. And thanks to our participants for all those great questions. This topic clearly resonates, and it seems that these best practices can go a long way to bringing awareness on what can be done to prevent these cold weather problems. Please note that our last and final winterization session will be held next Thursday, September 27th at noon Mountain Time, when Tristian McCallion will take a look at unit heaters. So for now, on behalf of everyone at Edmonton Valve and Fitting and the Swagelok Energy Advisors team, we'd like to thank you for participating in today's session and look forward to having you join us again next week. Bye-bye.